Thank you. So it's really a great pleasure to be here. I've heard so much about Alibaba over the years, and I've always wanted to visit, so I'm grateful for the chance to be here and tell you about the impact of quantum computing. So this is indeed a hot topic. It's been in the news quite a bit. So some of you may have seen this cover of Time magazine from 4 years ago now. It's a description of the so-called infinity machine, which is a quantum computer. Right? Each one costs $10 million, operates at 459 degrees Fahrenheit below zero, and most importantly, nobody knows how it actually works. Right? So a lot of mystery around this topic. And it's made some additional headlines. This is the Washington Post from just a few days ago, an article entitled, "This is the most important tech contest since the space race, and America is losing." And it was written by none other than the president of my own university, University of Southern California. So what's he worried about? Whoever gets this technology first will also be able to cripple traditional defenses and power grids and manipulate the global economy. The surest way to deter such behavior is to win the race. And China is pulling ahead. So that's why I'm here. Right? In the US, people are very concerned that China is winning the quantum computing race. Why is that? Because we heard rumors that the Chinese government is building a $10 billion facility for quantum computing. China has already launched the Quantum Experiments a space-scale satellite, which I know Alibaba was involved in to some extent. And in comparison to China's investment, the US has invested a paltry $300 million a year as of 2016. So the perception in the US is that China is pulling ahead. And on Saturday, I was at a workshop in Beijing in which I heard from Chinese investors that they're greatly concerned because the United States is way ahead of China in the quantum computing race. So this is very good for people like me who are working in this business. We like it when our respective governments are concerned, and we want them to keep funding us. Kidding aside, where did it all start? So quantum computing has its origins possibly with Richard Feynman, who is, as I'm sure you all know, a famous physicist, won the Nobel Prize for quantum electrodynamics. And he wrote a visionary paper in 1982 called Simulating Physics with Computers, in which he was proposing to use quantum computers. But actually, this story is not complete either. It may, in fact, be the first example of what we nowadays call Russian meddling or fake news, because in Russia, it wasn't Feynman who first proposed quantum computers. It was Yuri Monin, a mathematician, who actually first talked about quantum computers already in 1980, 2 years before Richard Feynman. Except, unfortunately for Monin, he did it in a radio broadcast, and so the credit ultimately did go to Feynman, who wrote things down. So what did Feynman propose, or what did Feynman discuss? His concern was simulating quantum mechanics. He made the observation that simulating quantum mechanics itself is a very hard computational problem. And so his idea was that we should build a computer out of quantum mechanical elements, which obey quantum mechanical laws, so that the quantum computer that he envisioned itself would be able to simulate quantum mechanics. Right? So this is what we nowadays call quantum simulation. It's the problem of using a computer, a quantum computer, in order to simulate quantum mechanics itself. That's the application that Feynman had in mind. That was a very visionary idea. He observed that classical computers are very challenged by simulations of quantum mechanics, and so his idea was, let's build a machine made out of quantum mechanical components which can simulate all of quantum mechanics by itself. Now, there's a different origin story of quantum computing. The Feynman version is the intellectual version, but another way to motivate why we're interested in quantum computing is this more traditional perspective of Moore's law. So what is Moore's law? As you probably all know, it's the scaling of the number of transistors per let's say, per centimeter squared as a function of time, and that scaling of the number of transistors has been growing exponentially for more than 50 years now. All right, so here's Moore, that's his law. Moore's law is still going strong. Actually, this graph goes up to about 2015, so maybe it's started to slow down a little bit, but what has already started to come to an end is what's called Dennard scaling. This is Dennard here. Dennard scaling is the scaling of other performance measures, not the density of transistors, but rather something like a speed measure, a single thread performance, or frequency, or power drawn by computers. You see that all of these are starting to flatten. And the response of the classical computer industry, as opposed to the quantum computer industry, has been to roughly double the number of cores per processor over the last several years. All right, so of course, this is not very sustainable. What's more, Moore's law itself is under threat, because if you think about the numbers involved, the silicon atom radius is 0.2 nanometers. The Ivy Bridge processor that is currently in use in Intel processors is 22 nanometers. That's 100 atoms, 100 silicon atoms. So we are already at an atomic scale. 100 atoms is atomic scale. Right? And the next chip on Intel's roadmap is half the size. So that's 50 atoms wide, and its dielectric thickness is only going to be 6 atoms. So at this scale, quantum mechanics is what matters, because quantum mechanics is, first of all, the theory of the very small, of atoms and electrons and so on. Right? So quantum effects are inevitable. Moore's law, continuing exponentially, is very soon, in a matter of essentially now, if not now, a couple of years, is going to reach the size, the scale at which atomic effects can no longer be ignored. Quantum effects can no longer be ignored. This was also anticipated by Feynman in a different paper. In 1981, he wrote famously, "It seems that the laws of physics present no barrier to reducing the size of computers until bits are the size of atoms and quantum behavior holds sway." All right, so this quantum inevitability is, on the one hand, a nuisance, a problem. On the other hand, it's an opportunity, because, as we're going to see, quantum computers offer a path beyond Dennard scaling. And what's more, they're much more powerful. And that's the story I want to tell you next. So, after Feynman, there was a period of more than a decade where nobody paid much attention. And then, surprisingly, in 1994, a mathematician by the name of Peter Shor, who's now at MIT, proposed a quantum algorithm for solving the factoring problem. So this is the problem of factoring integers into their prime components. And this is a problem that has very important applications in cryptography. If you can factor efficiently, you can break RSA, you can break public key encryption. Right? And what Shor was able to show is that when we compute using quantum mechanical laws, we get an exponential speedup in factoring. So the best classical algorithm for factoring for an integer that has n digits, this is a complicated formula, but basically it says that it's exponential in n. Right? If you want to factor an n-bit integer, you need a time that grows exponentially in the number of bits. But with a quantum computer, you can solve this problem in a polynomial time in only about order n cubed. Exponential speedup. So this has huge implications for cryptography. And then, only 2 years later, Love Grover, also from AT&T at the time, came up with another remarkable quantum result, and this is what we now call Grover's algorithm for search. So what is the problem Grover was concerned with? It's the problem of finding a marked item in an unsorted list. Right? So you can think of this as the inverse phone book problem. Whereas in the usual phone book problem, you are given a name and you're supposed to find a number. The inverse phone book problem is you're given a number and you're supposed to find the name. Right? Because the phone book is random with respect to the phone numbers, either you are supremely lucky and you find it on your first attempt, right? Or you're supremely unlucky and you find it on your last attempt. So on average, you're going to have to go over half the names in the phone book. So classically speaking, the best you can do is an algorithm that takes order n, or n over 2 attempts. But it turns out that if you had a quantum computer, you could solve this problem in time that scales only like square root of n. So this is a quadratic speedup. It's not an exponential speedup, but it's a remarkable speedup because it's a speedup for a problem that has no structure whatsoever. It's completely random. Right? There's no information here, and yet you can speed it up. Another very interesting and important example of a quantum speedup, if you had a quantum computer, is the problem of solving a linear system of equations. Right, so we all learn in high school how to do Gaussian elimination and solve linear systems, finding x when the vector x, when A is some matrix and B is another given vector. We know how to do that efficiently. We can solve it in time that scales like n cubed, where n is the size of the matrix. But even so, we can speed this problem up exponentially as well. Right? We can return the solution vector x in a time that scales like order log n. So solving linear systems is obviously a problem with very wide applicability, and it can be sped up exponentially on a quantum computer. This is due to Harrow, Hasidim, and Lloyd in 2008. And as a final example of an amazing quantum speedup, I want to mention the context in which Feynman made his original proposal, simulating quantum mechanics itself. So an algorithm due to Jordan, Lee, and Preskill shows that you can simulate quantum field theory. You can compute scattering probabilities, which are of interest to physicists doing high energy experiments, also with an exponential speedup. Right? So this result and others like it prove that the original idea that Feynman had was correct. If we have quantum computers, we can simulate quantum mechanics itself with exponential speedups relative to what we can do classically. Okay, so let me summarize some of the quantum killer apps. We have applications in cybersecurity. We can break public key cryptography using Shor's algorithm. And that is something that should worry us right now, even though we don't have quantum computers that can do this yet. If you're worried about keeping secrets and you want those secrets to remain safe for the next 50, 100 years, it's likely that we're going to have quantum computers within 10 or maybe 20 years that are going to be able to run Shor's algorithm, if not sooner. And so if you're paranoid about keeping those secrets, you should avoid using encryption algorithms like RSA, because they are going to be broken by quantum computers. So that has immediate applications for the ultra-paranoid. There's a flip side to this, which I won't go into except to mention it here, that actually quantum mechanics also offers a solution to the threat presented by Shor's algorithm, and that is that we can do quantum encryption as opposed to classical encryption. And the quantum encryption is provably secure as long as the laws of quantum physics are correct. Right? So we can protect against algorithms like Shor's algorithm that can break encryption, provided we do quantum encryption. This is an area that is already quite active in terms of commercial applications, by the way. There are companies that will sell you quantum encryption boxes. Next, the context for Feynman's ideas, simulations of quantum mechanics. If we can do this, what are the applications? Well, they are very important. For example, we can use the simulation of quantum mechanics in order to try to discover new pharmaceuticals, new drugs. You can imagine simulating the interaction between a virus and a molecule representing a drug on your computer rather than doing it in a test tube. We can also imagine trying to discover novel materials, exotic materials that rely on an interest in quantum effects like topological materials, superconductors, high TC superconductors, topological insulators, and so on. So here's an example of a paper that was published recently in which people applied these kind of ideas in the context of quantum chemistry. So you see a small molecular reaction that is being simulated here. This is on the IBM quantum computer. And then another killer app is optimization. So here we are on less safe grounds. We don't actually have strong results yet proving that we can speed up optimization problems, but we have high hopes that this is going to be the case. So by optimization, what I mean is problems like deep learning, verification validation, supply chain logistics, finance, and so on. So these are applications that I believe should be of great interest to a company like Alibaba. And I'll talk a little bit about the kind of quantum information processing devices that we have available. So all of this has been attracting a lot of attention. I already mentioned some of the reports in the media, but governments have taken notice worldwide. So here's the response from the US government. This is from a couple of years ago. A report was issued addressing national challenges and opportunities in quantum information science. And very recently, I know the print here is small, but a national quantum initiative was announced in the US. And it's going to have a budget of $800 million over a 5-year period. So that's a good start for the US. In other countries, the governments have taken even more drastic action. So, for example, in Europe, the quantum technology flagship project was funded about a year ago. And so the European Union has devoted 1 billion euros, which are being distributed over a variety of labs in the EU in order to fund quantum computing research. And then I already mentioned that reports are that in China, there's going to be a national lab for quantum information science, possibly in Hefei, funded to the tune of $10 billion. Right, so these are just some examples of governments taking notice on a substantial scale of the need for funding quantum information research. Now it's not just companies, also companies have, not just governments, also companies have taken notice. So for example, here is Satya Nadella, the Microsoft CEO, in his recent book. He wrote that the battle over quantum computing is an arms race as important as AI or virtual and augmented reality, though it has gone largely unnoticed. Right? And so this is the perception that we're trying to change here. Okay, so what is the source of all this quantum power? I've told you about a few algorithms and I haven't really explained how they work. I'm not going to go into the details of it, but I want to give you a little bit of an understanding of what is behind all this quantum power, how we can do information processing so much more powerfully than we can classically. It's not really fully understood yet, but we have some good ideas. And it all starts, in a sense, with one of the founding fathers of quantum mechanics. This is Erwin Schrodinger, and most of you have probably heard about the Schrodinger Cat experiment. So in the Schrodinger Cat experiment, we have a bit, which is represented by a cat, except now it's a quantum bit. The two states, we like to denote them by 0 and 1 in this way. So think of this as cat is dead, cat is alive. And what Schrodinger's cat represents, this is a thought experiment that represents how we can couple quantum mechanics and some of its weirdness to macroscopic phenomena like cats. And so in Schrodinger's thought experiment, here is quantum mechanics. There's a radioactive atom, which is quantum mechanical. And because it's quantum mechanical, when we can put it in a state where it emits radioactively, decays radioactively, and does not decay radioactively. This is the key. The key word here is the word and. It can be in a quantum superposition of decaying and not decaying. Right? If you want to take one message home from this talk, it's the difference between the word and versus or. Quantum mechanics is about and. The classical world is about or. In the quantum world, an atom can be in a superposition of both decaying and not decaying simultaneously. Of course, that doesn't exist in the classical world. But now Schrodinger proposed a way to couple this to the classical world of cats. The atom is decaying radioactively and not decaying. When it decays, it hits this trigger, which is attached to a hammer, which hits a bottle of poison. And if that happens, the cat is dead. If it doesn't happen, the cat is alive. So the fact that the atom is in a superposition of decaying and not decaying puts the cat through this chain in a superposition of being dead and alive at the same time. Right? And so there is a way through this thought experiment to couple quantum mechanical weirdness, superpositions, to classical phenomena. And of course, nobody's ever observed a cat that is both dead and alive, and you can ask yourself why that is, and it's actually a very deep question to which we don't really have a full answer yet. But one thing that will happen for sure is that if this is all happening inside a box and you can't see what's going on, you have to assume, provided quantum mechanics is correct, that this cat really is in a superposition of dead and alive. But when you open the box, you have destroyed that superposition. It has suddenly become dead or alive. So there's some effect that takes place, which is called decoherence, and I'll talk about it a little bit, that destroys these quantum superposition states. It tells us that superposition states are very delicate, and that's an important lesson for trying to build quantum computers using this effect. Why is this related to quantum computing at all? Why am I telling you about this and versus or? Because as soon as you can create a superposition state like this, you can imagine having many atoms, each one representing another bit or another quantum bit, another qubit. And when you have many of them, you can represent many different possibilities simultaneously. So the quantum superposition principle says that if you have n qubits, you can have a state representing 2 to the power n possibilities all at once. Right? So that is massive parallelism. And I would be lying if I told you that that's the whole story of the power of quantum computing, but it's a good place to start to try to understand what makes quantum computers powerful. It's the superposition of many different particles. So the superposition principle used to be, or the superposition idea used to be thought of as a mystery. Philosophers argued about it for decades, but nowadays we just think of it as a useful resource, a resource for quantum computing. So here's another way to understand a little bit more seriously what the power of quantum computing is, and it has to do with quantum dynamics. So let me pause this movie here. So on the left-hand side, what you're seeing is an attempt to solve an optimization problem classically. So what do we do classically when we try to solve hard optimization problems? You can often think of optimization problems as being represented by some landscape where the right answer is the global minimum and the wrong answer is some local minimum. So how does a typical classical optimization heuristic work? What you do is you have a random walker which is making random moves with gradient descent. Right? So when the gradient points down, you preferentially go down. When the gradient points up, with some probability you may go up, but most of the time you're going to go down. And you keep making random walk moves like this. So what happens with classical heuristics is that sometimes the particle ends up in the global minimum, but oftentimes it will end up in the wrong local minimum. Right? So this is like, imagine you're walking in the mountains, right, and you know that there's a treasure that's buried at the bottom of some deep valley. But you have no information whatsoever about where that valley is. All you can do is walk kind of at random on this landscape until you find the right valley where the treasure is buried. And how are you going to do it? Well, you're going to make random moves, just like this particle is doing. And every once in a while, you're going to decide, well, actually, maybe I should be going uphill, even though you see a valley right in front of you, because you suspect it may be the wrong one. And so using this kind of a random walk strategy where you also make up and down moves with a higher probability to go down than to go up is how you're going to try to find the treasure. This is simulated annealing. It's a well-known, well-established quantum classical heuristic for solving optimization problems. The problem is we often get stuck in the wrong local minimum. Now in quantum mechanics, we have a different option. Sorry. In quantum mechanics, we can do this. So we start, and I will not exactly explain how this works. We start from a flat landscape, and now we have a quantum wave function. This is like a quantum particle. Here, it starts on this flat surface. We slowly turn on the surface. We can do this quantum mechanically. The quantum wave function that describes the position of the quantum particle tunnels over, literally goes through this wall here from this position over to the position of the global minimum. So this idea of using quantum dynamics, which involves superposition states because the particle is found in many places at once, right? In fact, right here, it's in two places at once. It's in the wrong place and in the right place. And then this is the probability of finding it. That big peak is the probability of finding it in the right place. So this principle of superposition, which also, by the way, requires, in this case, it requires interference, wave interference, and tunneling, the ability of the particle to go through the wall that was being erected here, together allows quantum mechanics to solve optimization problems more efficiently than we can using classical dynamics. So of course this is very sketchy. I'm not telling you exactly how this works, but you have to trust me that the Schrodinger equation, the equation that describes quantum dynamics, is capable of producing just such phenomena. So there is some bad news. So decoherence is a problem that arises because any real quantum system interacts with its environment. And in fact, that's true not just of quantum systems. It's true of classical systems as well. I mean, this is the famous anthropology situation where the anthropologist is visiting an exotic tribe somewhere, and the mere presence of this person in the midst of the tribe is going to change their behavior. And the same thing happens in quantum mechanics. It's the interaction with the environment. Right? So imagine that you put a quantum computer in a superposition of two states. And now the environment can be anything that is outside of this computer. In particular, it could be some photon that is coming from outer space, right? Or a gamma ray. And it interacts with the quantum computer that is in a superposition. And as soon as that interaction takes place, this is like you opening the box to look inside to see if Schrodinger's cat is dead and alive, but instead he becomes dead or alive. The superposition decays and you just get one possibility. All it takes for that to happen is the interaction with just a single particle or somebody sneezing in the lab next door or something like that. It doesn't take much to destroy a quantum superposition. And so quantum computers are very delicate. These superposition states are very easily disturbed and destroyed. But yeah, and that is really bad news for quantum computation because it turns out there's a theorem we can prove that any sufficiently decoherent quantum computer can already be efficiently simulated using a classical computer. Right? So if you can efficiently simulate a quantum computer using a classical computer, then you don't need to bother with building it. You might as well use the classical computer instead. But there is hope. There's a whole theory of what's called quantum error correction. Quantum error correction is a method that allows us to protect the superposition states and the other effects that are important for the correct operation of quantum computers. I won't go into it, but I will say that, number one, it's inspired by the theory of classical error correction. For those of you who studied error correcting codes, many of the ideas in quantum error correction should be easily recognizable. Secondly, I'll say that we don't believe that quantum computers will ever be useful, built up to a large scale, unless we rely heavily on some form of quantum error correction. And in fact, quantum error correction is so dominant in the performance of a quantum computer that we speculate that probably something like 99% of the time and the space occupied by a quantum computer is going to be taken up by error correction. So it's a very important aspect of the whole story. It's possible to do it. That's the important thing. Okay, so to summarize, what's a quantum computer? The building blocks are qubits, which are any quantum system that can be in two different states simultaneously. There are many different proposals for this: superconducting, charge, flux or phase, trapped ions, neutral atoms, and so on and so on. The secret sauce of a quantum computer is that it takes advantage of quantum superpositions, and it uses interference. It requires extreme isolation from its environment so that decoherence doesn't get in the way. But even so, there's always going to be some decoherence. And to get rid of decoherence, we have to incorporate quantum error correction. Okay, so that's the one-slide summary of what a quantum computer is. Now, there are several different models of quantum computation, which I want to introduce briefly because I want to show you pictures of what actual quantum computers look like in a moment. But to understand the difference between them, we have to talk about the different models of quantum computation. There are more than just two, but I'll point at the two most important ones currently. So one model is called the circuit or the gate model. In this model, we have qubits, represented here by starting as in the 0 state, and then a sequence of gates. Every qubit undergoes a sequence of quantum gates, logic gates coupling the different qubits, and so on. So it's very much like an ordinary classical computer where a computation progresses through a discrete set of operations, one operation happening at a time, or maybe several operations happening simultaneously with some clock that's ticking. And then at the end, you measure every qubit. Another model is the one that I hinted at when I showed you the animation of the wave function tunneling. And this is called the adiabatic or the annealing model. In this case, what we do is there is no sequence of gates. Instead, it's a continuous time evolution. Typically, what we do is we want to find the global minimum of some complicated landscape, right? So here's what the treasure is. And what we do is we start with some very simple landscape, which we deform slowly over time. That's called adiabatic, until the quantum state finds itself in that global minimum. Right? So discrete time evolution, continuous time evolution. Here we're trying to stay in the lowest energy state, the so-called ground state. Here we make a computation that progresses through the space of all possibilities one step at a time. Now, in both cases, we can divide into what are called universal quantum computers and special purpose quantum computers. Universal quantum computers are, as they sound, they're general purpose. They're capable of computing any function that's computable. Special purpose quantum computers in the context of the circuit model are typically used to do the Feynman thing, quantum simulation, simulating other quantum systems. In the adiabatic model, again, we can have universal adiabatic quantum computers. We can also have special purpose quantum computers. And in this case, typically the context is the one shown here, which is optimization, finding the best answer out of several possibilities, right? Each minimum here represents an answer, and this is the best one. Okay, so with that in mind, let me now show you some pictures of actual quantum computers. What's out there nowadays? So here is a circuit model quantum computer by Google. This is not the latest model they have. This is an older model with 9 qubits. Every line here, every one of these lines is an actual physical qubit. The scale here is 500 microns. So these are not atomic, right? These are fairly large objects, but nevertheless, each one is a qubit. So I just want to dispel the notion that quantum computing has to happen with atoms or electrons or nuclei. That's not true. It can happen with fairly large objects, like 500 microns or so in length. This is a circuit of superconducting qubits. The material here is aluminum. It's superconducting. And the qubit is represented by superconducting states And I won't go into much of the detail here, but it's based on superconductivity. Superconductivity is very popular. It's also used in the IBM machine, IBM quantum computer, which any one of you can access right now. If you pull out your laptop, you can go to the IBM Quantum Experience website, create an account, and start running quantum computing experiments. They have a nice intuitive user interface, which allows you to drag and drop gates and so on. Again, these are superconducting qubits, so-called transmons. The same is true for Google. Another superconducting qubits company called Rigetti. It's a startup based in Berkeley, California. Also, transmon qubits, superconducting qubits. In all cases, we're talking about companies that have built superconducting quantum computers with about 50 or 70 or so qubits in them. Intel, another important player in this story. This is their 49 qubit chip. Again, superconducting qubits. Right. Not everything is about superconducting qubits. There's a company called IonQ, which is using atomic ions. You can barely see them over here. Every ion is a qubit. The superposition states here are states of two different energy levels of an ion. All of these so far implement the circuit model. They attempt to become eventually universal quantum computers. They can also be used for simulation. And one more company I'll point out in the context of the universal or circuit model type approach. That's Microsoft. Microsoft is betting on an approach called topological quantum computing. If it works out, they will have to do a lot less error correction, quantum error correction, than everybody else. Topological qubits are highly robust against decoherence. Okay, and so that's a very interesting and, however, risky approach. It's risky because right now they still haven't demonstrated that they actually have qubits, but one day they will. Finally, I want to mention DWave. So DWave is, out of the entire set of companies that I've shown you here, is the only company that has decided to invest in the alternative approach of adiabatic or quantum annealing type quantum computing. So DWave is not implementing the circuit model, it's implementing quantum annealing. It's not implementing a universal quantum computer, it's implementing a quantum optimizer, a special purpose machine used for quantum optimization, right? So they're distinct in that regard. They're also the oldest company in the business of quantum computing. They've been around since about the year 2000, and they also have built the largest system so far. This DWave chip right here has more than 2,000 qubits. The other ones are at around 50 or so. So I want to say a few more words about DWave because at USC, we actually have one of those machines. And this is to give you a sense of the scale of the machine. It's a fairly large box. So when you open it, what you see is one of those little chips inside. It's surrounded by a lot of extra equipment, dilution refrigerators, magnetic shielding, and so on. And at USC, we've had a DWave machine thanks to a collaboration with another company, Lockheed Martin. They're well known for the F-35 fighter jet. They're an aerospace company. They were interested in quantum computing early on. In fact, thanks to Lockheed Martin, we have had a DWave quantum annealer since 2011. And it started with a 128 qubit machine, which was then upgraded to a 512 qubit machine 2 years later, upgraded again 3 years later to an 1152 qubit machine, and that's where we are right now. We have the DWave 2X. In the meantime, Google got into the game a couple years after us. They started with this DWave 2 and installed it at NASA Ames in Northern California. And they upgraded to the 2X, and then they did another upgrade to DWave 2000Q, which is the machine I mentioned earlier that has more than 2,000 qubits right now. And that's so far, the largest quantum annealer, quantum information processing device that's been built and sold to anyone. And there are several other players. Los Alamos National Lab has a DWave 2X. There's a company called Temporal Defense Systems that apparently has a 2000Q. Oak Ridge National Lab and the University of Toronto have cloud access to these DWave machines as well. So there are quite a few entities that are considering and studying the DWave machines, and there's a lot of interesting things that one can do with them. So I want to give a plug here for what's happening at USC. As I mentioned, we have this USC Lockheed Martin Quantum Computing Center. We have benefited from the generosity of Lockheed Martin by their investment in 3 generations of these DWave quantum annealers. And we've also learned a lot of lessons from studying the DWave machines. In fact, the US government decided after all the studies that were done on the DWave machines to invest in an alternative program to start studying quantum annealers like the DWave machine, but to start from scratch. And this is under the so-called Quantum Enhanced Optimization Program, or QEO. It's funded by IARPA. And the goal of this program, which is headquartered at my university at USC, is to find out whether we can improve on the designs of DWave, whether we can take a different route, and discover ultimately whether we can have quantum speedups using these types of machines. And I'll tell you a little bit more about what we've found so far with the DWave machines. So this is a large-scale collaboration, involves many universities and 2 companies, Lockheed and Northrop Grumman, and also a very strong contribution from MIT Lincoln Lab, where we are actually manufacturing the qubits that are going to be used in this program. Okay, so now I want to talk about the impact of quantum computing, the scientific impact of quantum computing. And so let me divide this into the short term and the longer term, and I'll just artificially call it less than 5 years, more than 5 years, and let's see where we are. All right, so first of all, let's go back to the question of factoring. Factoring was Shor's algorithm, the algorithm, the discovery that really drove the beginning of the quantum computing story. So where do we stand? The state of the art in factoring currently, using 5 trapped ions, so 5 qubits, in an experiment like the one shown here, in a paper that was published a couple of years ago from Rainer Blott's group in Vienna. Do you believe this? Well, quantum computers will tell you with 99% confidence that it's true. Okay? This is the state of the art of factoring today. So we're not very far yet. Okay? Quantum computers are not very good at factoring yet. Actually, they're a little better than what I'm telling you, because 143 has also been factored. And I don't recall the percent confidence, but I think it was less. But it's been done. Unfortunately, this was done using a technology that we don't believe is scalable, liquid state nuclear magnetic resonance, whereas the trapped ion approach is believed to be scalable. So factoring, the bottom line is, even though we know that it's a real killer app for quantum computing, it is still very far away from being a realistic threat to current cybersecurity. Okay, we're still only capable of factoring very small numbers, and it's going to take a few years before we get to numbers that are truly interesting. So in the meantime, we can focus on more near-term goals that are attainable. And that has to do with what we can do with quantum annealing. So quantum annealing, what can we do with it now? We can solve optimization problems that you would not be able to solve in your head, or that even on a laptop would give you some trouble. Right? Whereas factoring, you can solve the factoring problems you can solve on a quantum computer in your head in about a picosecond. But not true for for optimization and what we can do with quantum annealing. So what is the optimization problem? In this case, we want to find the lowest energy spin configuration of a spin glass. This is just physics speak for trying to find that treasure in the valley. Right? But I will tell you that these spin glass problems, they are notoriously hard, they're NP hard, and solving them is unlikely to ever be done in less than exponential time. So we took a look at this problem. This is using the DWave 2000Q processor. And in a recent preprint, we studied a certain type of randomizing spin glass problems. So these are random optimization problems that have random structure, but also have frustration, if you're familiar with that terminology. And here's what we found. So if you look at the time to solution, that's TTS, the time to solution, the time it took to find the solution, to find the global minimum, as a function of problem size. Here, the number of qubits is 8 times this quantity squared. So at this scale, we're talking about 512 qubits. At this scale, we're talking about 2,048 qubits. So if we look at the time it took to solve these problems as a function of problem size, and notice this is a log scale, so a straight line here is exponential growth in L. On the DWave machine, what we found was that it was exponential, but it has a slope of 0.76. Whereas if we use simulated annealing, which is this heuristic where you make a random walk on the energy landscape and do gradient descent, which is a very powerful general purpose heuristic, the slope was higher, right? The slope is 1. It's accidental that it's 1.00. Don't read anything into that. The point is, the scaling, which is the slope of this curve, was less on the DWave machine than using simulated annealing. And please ignore the other one. It doesn't matter. Right? So this demonstrates a scaling advantage on problems involving 2,000 variables. Right? These are very difficult problems to do in your head. On a laptop, you can still do them, but it takes a lot of time. We saw a scaling advantage for a quantum annealer relative to a state-of-the-art classical optimization approach. And that's significant. Unfortunately, when we used a different classical heuristic, not simulated annealing, something called simulated quantum annealing. It's a classical algorithm that tries to simulate the behavior of a quantum annealer. We found a slope that was flatter. Right? So whereas with a physical quantum annealer, with the DWave machine, we were able to beat simulated annealing, the machine lost against a different classical algorithm known as simulated quantum annealing. Okay, so the bottom line is that there's some good news here, a scaling advantage relative to a powerful heuristic. There's also bad news. The quantum annealer is still losing against another classical algorithm. And this is kind of a general lesson in this business of what we call benchmarking quantum algorithms. At least with the DWave machine so far, whenever we find a speed up relative to one classical algorithm, we tend to find that there is some other classical algorithm that does even better. Right? And so it's an arms race. Still, we're hopeful because this indicates that there are certain problems, the ones that we studied here, for which we are already seeing a partial advantage. It's good news. So here's another application, what we can do with quantum annealing today. And this has nothing to do with speed up. Everything I've talked about so far in terms of quantum computing were advantages related to speed up. But we can also try to ask a different question. Like, can we do machine learning and train a machine learning algorithm on a quantum annealer to have higher accuracy? Never mind the speed, focus just on accuracy. Can we get better accuracy using a quantum annealer? So in this case, because I was on sabbatical at Caltech and collaborated with a high energy physicist there, we looked at a problem that comes from the world of high energy physics, namely identifying the Higgs boson. Right? And in this case, for those of you who know a little bit of Feynman diagrams, you see a Higgs boson here decaying into two photons. And at CERN, where they perform these kind of experiments where they discover the Higgs boson, they look at the signal from these two photons and they decide, based on the properties of these two photons, whether they originated from a Higgs decay event or from something else. So this is the kind of experiment that they performed at CERN in order to find the Higgs boson. And as you can imagine, CERN has spent considerable resources on trying to detect these kind of events. And the way they actually do it is they use machine learning algorithms. So we decided to train a machine learning algorithm on the DWave chip. And in this paper that was published last year, we showed that if you look at the classification accuracy, so this is basically a measure of, did you correctly identify a Higgs boson event or not? That's the classification accuracy. It's technically the number of the number of true positives versus the number of false positives. That's the classification accuracy. So classification accuracy of 1 would be only true positives. If you look at that as a function of the size of the training data set, right? So when you train a machine learning algorithm, you have some training data set. What you're seeing here are the accuracy versus training data set, but this is the accuracy not on the training data, this is the accuracy on the test data, right? So first we train for different sizes, and then we look at the test data set and see if we can correctly identify the Higgs event. And what we found was that, it's hard to see here, but QA is the DWave result, QA for quantum annealer. Here is the quantum annealer curve, and here are deep neural nets and XGB, which is boosted decision trees. So two state-of-the-art machine learning algorithms, deep neural nets and boosted decision trees, performed worse for small training sizes. Right? So with the DWave chip, we were able to achieve higher accuracy than deep neural nets and boosted decision trees for small training data sets. For large training data sets, deep neural nets and boosted decision trees perform better. Right? So the message here is, for reasons we don't fully understand, small training data sets favored the quantum annealer type approach to machine learning over these state-of-the-art. These were the actual methods used at CERN, deep neural nets and boosted decision trees. The quantum annealer did better. But again, that's not the whole story, because you may have noticed there's another curve here. SA is simulated annealing. Simulated annealing, the same algorithm that I told you was beaten here, right? That was the red curve. Here, in this context, simulated annealing performed indistinguishably from DWave, right? So the real message here is that using this type of approach, this annealing approach, we accidentally discovered a method that was better at doing the machine learning task of identifying the Higgs boson, provided the training data set was small. And it didn't matter whether we used a quantum annealer or a classical annealer to do it. Annealing did better than these other methods. So this is just to give you a hint of some other things that we can do with current quantum computing technology and how it sometimes inspires accidentally a discovery in classical methods. We did not anticipate that simulated annealing would outperform these state-of-the-art machine learning methods, yet it did. So now let me move on to some other topics in the short-term impact of quantum computing. And I want to talk briefly about quantum simulation and quantum supremacy. Okay, so quantum simulation, once again, is this Feynman vision of quantum computing. We use a quantum computer to demonstrate, to solve a problem in quantum mechanics itself. So here's an example of this. This is trapped ions. Every single little dot here is actually the fluorescence from a single ion that you're observing, right? So you're looking at atoms, one atom at a time. They can be resolved. And the problem that the group of Chris Monroe at the University of Maryland studied was a physics problem. This is, after all, quantum simulation. It's the quantum phase transition from a disordered paramagnetic phase to an ordered anti-ferromagnetic phase. And I won't go into the details because I know that very few of you are physicists, but I'll just point out that what you're seeing here, correlations between ion number 1 and ion number 1 plus r as a function of the distance, so correlation between this ion and another ion. You see a transition from a paramagnetic phase where there are no correlations, that's the red curve, to this anti-ferromagnetic phase where their ions are anti-correlated. And the point here is that doing this kind of simulation is very hard to do on a classical computer. This is what Feynman realized or pointed out. Yet we now have systems that can do this kind of a simulation. Right? And we know that doing this simulation on a system that involves more than about 50 particles is already intractable on a classical computer. And we're not far from being able to do that using these quantum systems. Right? So quantum systems are very close to the point at which we will be able to use them to do quantum simulation in a regime that is not accessible to classical computers. Right? So the Feynman vision of quantum computing is very close to being realized. I think it's a matter of certainly less than 5 years before we get to the point. And once we do that, this will have serious impact, because it's exactly these kind of simulations that are going to be needed in order to discover new materials, as I mentioned earlier, maybe even at a later stage, to do something like first principles discovery of new pharmaceuticals. Now, quantum supremacy. This is something that you may have heard about in the popular press. It's a very hot topic nowadays. So what do we mean by quantum supremacy? It's actually not that different from what I just talked about in the context of quantum simulation. It's essentially being able to do something on a quantum computer that would be intractable for a classical computer to do. But there are two twists here, two wrinkles. One is we're willing to demonstrate this on a task that is even possibly useless. So for quantum supremacy, we don't care about whether you're solving a practically important problem. Quantum simulation is practically important. But in quantum supremacy, we're willing to just show a speed up on anything, even if it's a completely random problem of no particular practical interest. Secondly, it is set up in such a way that you can show that if you could do this task on a classical computer, it would have dramatic implications for what's called the polynomial hierarchy of computer science. So it would, if a classical computer would be able to perform this kind of task, it would lead to the collapse of the polynomial hierarchy. It would be something like P equals NP on a classical computer. This is how these problems are set up. So we know that if a quantum computer can do this, it is very, very unlikely that a classical computer would be able to do the same, or else P equals NP. Right? So this is how we set up problems in the quantum supremacy context. And that has both foundational and practical implications. Right? It would refute the extended Turing thesis, and it would also greatly increase our confidence, if we can do this, that quantum computers are just around the corner. So let me give you an example of quantum supremacy. And you will recognize this circuit from before. This is the 9-qubit chip due to Google. And the Google group has proposed a particular quantum supremacy experiment. So the proposal is to sample from the distribution that is generated by a random quantum circuit. As I mentioned, it's not a practically important problem. A random quantum circuit just computes something completely random. Okay. But it was shown that this proposal of sampling from a random quantum circuit is sharply hard, meaning you're not going to be able to do it efficiently on a classical computer, right? So if you can do this on a quantum computer, chances are it's impossible for a classical computer to get the same answer in the same amount of time. So specifically, this is the kind of setup. This is one time slice of the circuit. The red dots are qubits. Every red dot also represents a single qubit gate. And then the blue lines are 2 qubit gates. They're called ZZ gates. And in the next time slice, you flip all the ZZ gates. Here they're vertical, here they're horizontal, and so on and so on. And the 1 qubit gates are random gates. That's why it's a random quantum circuit. Every single qubit gate is random. So it turns out that, as I said, computing the output of such a circuit is essentially a classically impossible problem. But if you run it on a quantum computer, you might hope that it's going to do it well. And so if you can do this on a large enough scale, you will reach the point where classical computers are not going to be able to reproduce the answers computed by the quantum circuit. And Google hopes that it's going to use its current 72 qubits chip to demonstrate this kind of quantum supremacy experiment in about a year or so. Right? The original estimate for this to be classically intractable was for about 50 qubits or so. But actually, the goalpost has been moving, actually due to some papers from not far from here. A paper from, February from USTC showed that, contrary to earlier expectations, this problem was actually maybe not so hard for classical computers. They showed that a 72 qubit circuit of depth 22, so depth is the number of gates that are being applied, could be simulated in a few days on a supercomputer. Right? And then the group of Yaoyun Shi here, in collaboration with Jiangjin Chen, who's the first author of this paper, showed that a 64 qubit circuit with depth 40 can be simulated in 2 minutes on the Alibaba computer cluster. Right. So Alibaba has played an important role in pushing the quantum supremacy goalpost. It's an arms race. We know that eventually quantum computers are going to reach a scale where this kind of quantum supremacy experiment is not going to be feasible for classical computers. But currently, we may still be at a scale, 64, 72 qubits, and so on, under 100 qubits. It seems that classical computers are still going to give quantum computers a run for their money. But I'm willing to bet that above 100 qubits, once they are sufficiently coherent, in other words, not decoherent, at this point, it's very unlikely that classical computers, even the Alibaba cluster, is going to be able to keep up. Right? So quantum supremacy, the race is on. However we achieve it, once it's achieved, this will mark the beginning of a new era in quantum computation. It will be the beginning, really, of an era where quantum computers can solve problems that cannot be solved on classical computers. I predict it's less than 5 years away. So what about the longer term? Well, does anyone have one of these? I don't have a crystal ball, so the best I can do for you in terms of the longer term is I can ask an oracle. Right? So the best oracle I know is PageRank. And I discovered that actually this doesn't work here. Right? So we have to go to a different oracle. This one. So if you go to Baidu and you type in this phrase and you hit tab, at least as of some time ago, the first answer that comes up, don't try this in real time, is this. And the second answer that comes up is this. Okay? So, of course, they're both right. Right? So we know that. The real answer is a superposition of both of these things. But when you open the box, there's only one answer that's going to survive, this one. Thanks.